Hello, in this video we're going to be talking about some of the exceptions to traditional stages of sleep. What are some of the drugs that help people with sleep disorders sleep? And then also understand the two biological theories of dreaming. So the first question is, does the brain sleep all at the same time? So thinking about those different stages of sleep that we talked about, are those all happening at the same time, or are they compartmentalized in different parts of the brain? So most of the time students say that the brain doesn't sleep all at the same time because we dream or there's sleepwalking. But in most cases, the brain is all asleep at the same time. So when we're saying here in most cases, that means, of course, if this is most cases, there are exceptions to the rules. So what do you think some of those exceptions are? I think maybe we've talked about some of them previously in this semester. Well, one are certain animals. So what animals do you think might have one half of their brain or one hemisphere of their brain sleeping while the other one's awake? And that's what you can see here. So here you can see these large slow wave sleep waves or delta waves. And you can see here it's recording in 1, 2, and 3. So in this hemisphere, the left hemisphere of the animal, 1, 2, and 3, we see the animals in deep sleep. And here, the animal's awake. In this hemisphere, in the right hemisphere, 4, 5, and 6, 4, 5, and 6, we see the animals awake. Now, at another recording, we see the opposite. We see this hemisphere is awake and this hemisphere is asleep. So what animals would that be important for this behavior to occur? What about a dolphin? Why would they need this behavior to occur? Or a shark? Or a whale? Yeah, so they come to the surface and get their oxygen. They have to come to the surface, I think it's approximately every 16 minutes in order to breathe. And so half of their brain is keeping them awake so that they remember to do this while the other half sleeps. We also see it, certain birds have the ability to, when they're migrating, to change their sleep cycles and things like that. We also see it in individuals who are sleepwalking. So sleepwalkers are actually awake in part of their brain and asleep in the other. This doesn't typically occur in REM sleep. It typically occurs in stage 3 sleep or that deep sleep. And so again, because in REM sleep, those pons are sending a message to inhibit those postural muscles so we don't act out those dreams. So sleepwalking is typically occurring in stage 3 sleep and is when part of the brain is actually awake. Another exception that some of you may have heard of and some of you may have not is called lucid dreaming. So lucid dreaming is when you're aware of your dreaming and you can actually potentially control your dream. This is actually normally a really fun discussion during this class, but since we've moved to video, I've made a discussion assignment for you. So there's a link in the PowerPoints that you can also go straight to the discussion board, and you'll see there's a video there, short video there for you to watch, and then a couple of discussion questions for you to respond to. So please make sure after you're done watching this video that you go on and you complete that discussion assignment. So now we're going to talk about drugs that help us to sleep. And the most classic sleep aids are these benzodiazepines. So benzodiazepines are GABA agonists. And so what that means is that they mimic, this term agonist means that it mimics GABA or it acts like GABA. And you can see down here, we have this GABA receptor and it has different binding sites. We have one here, this is where GABA binds. So GABA binds there, it opens up a channel for chloride to flow through and it inhibits the receiving neuron. Now, benzodiazepines don't bind in the same spot. They bind in a separate spot and they modulate or alter the activity of the GABA, either increasing the time that chloride can go through or increasing that channel width so that more chloride can go through at the same time. You can also see we have an ethanol binding site and a barbiturate binding site, but the ones we're interested in now are for benzodiazepines and GABA. So overall, like I said, they increase the inhibitory effect of GABA. And the typical ones that are used for sleep aids are short-acting. And so, while we don't have the time to go into the differences here, is that benzodiazepines have short-acting and long-acting drugs. And the short-acting ones are things like Restoril or Halcion, and those are kind of your more common sleep aids. Now, some of the longer-acting ones, like Ativan or Xanax or Valium, that are more often prescribed for anxiety, sometimes are used as sleep aids, but only in extreme circumstances. We also have the Z drugs, and so Z drugs are also GABA agonists. So they're also mimicking GABA, but they do so perhaps by binding a different site and supposedly being a little bit less addictive. So some of these maybe are names you're a little bit more familiar with because they are considered to be less addictive. Lunesta, Ambien, Sonata. I know I hear commercials for those all the time on the TV. And there's also, there's lots of different classes of sleep aids, but there's a newer one it's an orexin antagonist. And I think I mentioned it in one of the previous videos, where it actually is blocking that effects of orexin. And remember, orexin is released from that hypothalamus and is then going to stimulate that basal forebrain, keeping us awake and arousing us. So if this antagonist blocks the effect of orexin, it's keeping orexin from doing its job and allowing us to sleep. So Belsomra or Suvoxrant, you may or may not have heard of Belsomra. And so that's working on orexin versus working directly on the GABA receptor like these other drugs do. So now we're going to talk about biological theories of dreaming. So later on, after you're done with this video, there's a short little activity that will take you through 2 other videos. One will talk about theories of why we sleep, and the other one will talk about theories of dreaming. But these are specifically the biological theories of dreaming. So what happens in the brain that causes us to have the dreams that we have? And so we're going to talk about 2 of them that are discussed in your textbook. The activation synthesis hypothesis and the clinico-anatomical hypothesis. So we're going to talk about 2 of them that are discussed in your textbook, the activation synthesis hypothesis and the clinico-anatomical hypothesis. So the activation synthesis hypothesis says that dreams begin with those PGO waves. And where do those PGO waves start? With spontaneous activity in the pons. And remember, those pons are going to be inhibiting our postural muscles. And a lot of times in our dreams, we have this feeling that we have this inability to move. And that's a common theme in dreams. Also, those pons are going to be stimulating other parts of the brain, in particular that cortex. And so when you're activating many parts of the cortex feels this need, this is the part of the theory, to synthesize that into forming a pattern. And that's why the stories don't always make sense, because we have these different parts of the brain that are being activated, and then it just synthesizes a story from that. So again, that's the activation synthesis hypothesis. The clinico-anatomical hypothesis has less emphasis on the pons in REM sleep, because remember, not all of our dreaming occurs during REM sleep. But it suggests that dreams begin with arousing stimuli that are just generated within the brain. As we're sleeping, we still have input from our senses. We can still hear things and smell things like that. And the parietal cortex is highly active, if you remember that from one of those previous slides that we talked about. And that activity combined with recent memories then gets synthesized into a dream. So stimulation from the environment combined with our recent memories gets synthesized into a dream. And so evidence to support this clinical anatomical hypothesis is that we have activity that is high in the inferior parietal cortex, which is important for visual spatial information. So if you remember earlier, in an earlier video, we talked about how this parietal cortex has a lot of activity, especially in REM sleep. We also have activity in the prefrontal cortex being suppressed. I also mentioned that this might become important when we talked about dreaming. So if you think about, when we get to the memory section, we'll talk more about how the hippocampus is important storing memories, but we think that eventually those memories get moved into the prefrontal cortex. So if you have activity of this area being suppressed, that could be why it's difficult to remember these dreams once we wake up. We also have activity high in the hypothalamus and amygdala. And do we remember what this amygdala is important in? Emotions, right? And so in the hypothalamus, it drives that are vital to survival. So that's why a lot of times our dreams have this very emotional content to them. So that activity accounts for the emotional activity and the motivational content of our dreams. So that concludes this video. Now you'll go on and do the lucid dreaming activity. There's a couple other videos for you to watch, a little assignment for you to do on the theories of why we sleep and the theories of why we dream. and then you'll finish up this module with a Kahoot on sleep disorders. All right?